In this lecture, we are going to solve next problem on step response of a second order system. So this is another type of problem that we can have based on the step response of second order system. As we solved in a previous lecture, a problem where the transfer function is directly given, but we may have question where the differential equation of the system will be given to us, and based on that we need to determine the time response specification and expression of output. So here we are having the differential equation of the system is given in the form of d square y by dt square plus 7 dy by dt plus 36y is equal to 10x. So this is the differential equation of the system is given to us, and in the question it is asked to determine the time response specifications and also the expression for output with unit step input. So whenever we are having differential equation of the system given to us, so we need to first find the transfer function. We know that how to find that. What we have to do, we have to take Laplace inverse of this equation, and based on that we can get the transfer function. So first step here will be to get the transfer function. So for that we need to take Laplace transform of the differential equation of the system. So by taking Laplace transform of differential equation, so it will be Laplace of this equation d square y by dt square plus 7 dy by dt plus 36y, and that will be equal to Laplace transform of 10x. So we know that how to take the Laplace transform of differential equation. So it will be s square into y of s. So while taking Laplace transform, we know that this term will going to give us initial condition. So in finding the transfer function, we treat those initial condition to be 0. So next the Laplace transform of this term will be 7s into y of s, and for this last term here it is 36 y of s, and for right hand side it will be 10 x of s. So now from left hand side we can take y of s common, so it will be s square plus 7s plus 36, and outside bracket we will be having y of s, and it will be equal to 10 of x of s. So here this y of s represent the output and x of s the input for this system. This we know based on the differential equation that we are having. Now to write the transfer function, it will be output, that is y of s upon x of s. So it will be 10 divided by s square plus 7s plus 36. So this is how, based on the differential equation, we can get the transfer function of the system. So now next step, what we have to do, we have to rewrite this transfer function in standard form. So standard form, we know that it is omega n square upon s square plus 2 zeta omega n s plus omega n square. So transfer function for this system will be 10 by 36, in bracket we will be having 36 upon s square plus 7s plus 36. So now this is the standard transfer function. Now we write in this way in order to get the natural frequency of the system and damping ratio of the system. So by equating, we'll get omega n square is equal to 36, and based on that we'll get natural frequency to be square root of 36, that is 6 radian per second. Now same way, to get zeta we need to equate this term with 7s. So it will be 2 zeta omega n is equal to 7. So from this one we will be having zeta is equal to 7 divided by 2 into omega n. So it will be equal to 7 divided by 2 into omega n we got as 6. So when we divide 7 by 12, it will be 0.583. Now once we got natural frequency of the system and damping ratio of the system, we can determine the damping frequency, and that we calculate by formula omega d is equal to omega n under root of 1 minus zeta square. So it will be 6 under root of 1 minus 0.583 square. So if we calculate this term, it will be 4.87 radian per second. So after determining the natural frequency, the damping ratio and the damping frequency, Now we can determine all the time response specifications. So let's find that. So first one is delay time, that is TD. So it is given by 1 plus 0.7 zeta divided by omega n. So we can substitute value of zeta and omega n here to get the value of TD. So it will be 1 plus 0.7 into 0.583 divided by the natural frequency we are having as 6. So we'll get this value to be 0.234 seconds. So based on this value, we can say that this system requires 0.234 seconds to reach to the 50% of its output. Next term is a rise time, which is given by TR, and expression for that is pi minus theta divided by omega d. So here we know the value of omega d. We have to find what is theta. So we know that theta is given by tan inverse of under root of 1 minus zeta square divided by zeta. So we can substitute zeta value here to get the theta value. So it will be tan inverse of under root of 1 minus 0.583 square divided by 0.583. So when we determine, we get value as 0.9483 radian. Now once we got theta, we can determine TR. So TR is equal to pi minus theta value we got as 0.9483 divided by omega d we got as 4.87. So once we calculate, we get value as 0.450 seconds. So based on TR, we can comment that system requires 0.45 seconds to reach to the required output. The next term that we have to determine is peak time given by TP. Formula for that is pi by omega d. So it will be pi by 4.87. So once we calculate, we get value as 0.645 seconds. So based on TP, we can say that system requires 0.645 seconds to reach to the first peak of the response. Next we have to determine is maximum percentage overshoot is given by percentage MP. The formula for that we are having as e raised to minus zeta pi divided by root of 1 minus zeta square, and this whole term we need to multiply by 100 to get into percentage. So let's substitute the value. So it will be e raised to minus 0.583 into pi divided by under root of 1 minus 0.583 square, and this entire term we have to multiply by 100. So once we calculate this value of e raised to term, we are going to get 0.1049, and that we have to multiply with 100. So it will be 10.49%. So maximum overshoot for this system we got as 10.49%. Now next thing that we have to determine is settling time. So it is given by TS, and formula for that we are having 4 by zeta omega n, and it is for 2% of steady state value. So it will be equal to 4 by zeta we got as 0.583 into omega n we got as 6. This value will turn out to be 1.1435 seconds. Based on this value, we can comment that system needs 1.1435 seconds to go within the 2% of the steady state or the required output. So last thing that we have to determine here is C of t, that is the output expression. So we know that the formula for C of t is 1 minus e raised to minus zeta omega n t divided by under root of 1 minus zeta square into sine of omega dt plus theta. So the transfer function that we are having for system is y of s upon x of s, and that is equal to 10 divided by 36 divided by s square plus 7s plus 36. So this is what we are having the transfer function of the system in standard form. So when we want to find the output equation considering the step input, so we can write this C of t for this expression as C of t will be equal to this constant we will be having as it is 10 by 36, and for this term we need to write this equation. So it will be 1 minus e raised to minus 0.583 into 6 into t divided by under root of 1 minus 0.583 square into sine of omega d we got as 4.87 into t plus theta we got as 0.9483. So here we need to calculate this value and this value. So it will be, we can also reduce this constant to 5 by 18 in bracket 1 minus e raised to, when we calculate this value it turned out to be minus 3.498 into t divided by, if we calculate this root value it will be 0.8124 into sine of 4.87 t plus 0.9483 we will be having as it is. Now this one we can further simplify as 5 by 18 1 minus, now this term in denominator we can take it to numerator, so we have to divide 1 by this value and it turned out to be 1.23 into e raised to minus 3.498 t into sine of 4.87 t plus 0.9483. So this is the output equation for this system. So by using this output equation we can determine the response of the system at any given time. So in this way, if we are having the differential equation, we can solve for finding the various parameter of time response specification, as well as we can determine the output equation. So let's summarize what we got here as answer. So we got first TD, that is delay time, 0.234 seconds. Then we got rise time, that is TR, 0.45 seconds. Then third, we determine peak time, that is TP, 0.645 seconds. Then fourth parameter we determine percentage overshoot, that is 10.49%. After that we determine settling time, that is TS, and we got value as 1.1435 second, but this value we determined for 2% of steady state. And last we have determined the output equation, that is C of t. So with this we'll end this lecture.